Hello, everyone. This is Mr. Ponce again, and this is part 3 of going ahead and using a V versus T graph. Now, last time I saw you, we actually went ahead and we found the equation of this V versus T graph, which was V equals to A for acceleration times time plus V naught, or V initial. In other words, my V at time 0, just so you remember. This is my V at time 0, right? And we use this to go ahead and find any future values of V. In other words, I can plug in numbers like 70 here, and I can figure out, if this graph were to go on forever, what my velocity would be. Okay, this sounds all good and well, but obviously there's more we can do with this. Unlike other things that we've dealt with, there's actually more meaning in a V versus T graph than there is in the X versus T graph. Now, one thing I would like to point out here is, while this is all linear, meanwhile, in the V versus T graph world, your X versus T graph world, right? So this may be linear, but in X versus T graph right now, you have a parabola. Now, according to this, you start going up, and you're actually remaining up because your acceleration here is a positive one. So your X versus T graph is going to look like something like this. And you're going to notice, if we were to look at the X versus T graph, right? So I'm just noticing here, this is a positive velocity, right? Because we have a positive velocity here and also a positive acceleration, right? We are covering more and more ground as time goes on, and we're just zooming up. Well, this is actually a form of a parabola, and you're going to notice that here. However, we can actually go ahead and we can figure out how much displacement we're covering. Now, here it's actually pretty easy, but in order to find the equation that would make this work, we actually need to go back to the V versus T graph, and that's actually going to help us a lot in terms of finding out what we need. Now, I'm just going to go ahead and grab something here. These are my notes. We're actually going to go ahead and look into a V versus T graph, and we're going to find out how we can figure out how much displacement is made due to acceleration. So I'm going to go ahead, I'm just going to scroll down a little bit, and we're going to do like the oldest trick in the book, right? And that is actually just taking a portion of this graph, right? We're going to do this. Now, if you remember, if we were to go ahead and take the slope of this graph, in other words, if we were to divide the values of, let's say you have here delta V and delta T, and if we were to divide the two, so in other words, we got delta V divided by delta T, that would ultimately give us an acceleration, right? Delta T. This ultimately gets us an acceleration. What we can do here, but we couldn't do back in an X versus T graph, is something new. What if we were to go ahead and, instead of dividing the two, let's go ahead and multiply the two. And if you get delta V times the delta T, you notice this does not get us necessarily, well, this actually gets us something. Where, right? If we were to go ahead and figure out how much time divided by the velocity, we can actually find a displacement, right? It's going to get us meters, which means some sort of displacement value. In other words, this means that the area underneath this curve means something. So this is area under curve. So this is area, so under curve. Forgive my handwriting with this thick pencil. Okay. So if we can find the area under this particular format, and we can create an equation for it, it means that we can go ahead and figure out our displacement value. Now, this is obviously a trapezoid, and that does make it difficult because we have several values we do need to be considerate about. And you notice, even if I'm using delta V here, it's like it does make it difficult. So what we're going to do is actually we're going to be a little smart about this, and we're going to actually divide and conquer here. The way we're going to do it is that we're going to go ahead and between these two bounds of t, we're going to divide it into two different areas. We're going to call this A1 and A2, where if we were to go ahead and add these up, you would get the total area and therefore the total displacement that is covered within these bounds. Let's go ahead and try this. Let's go ahead and solve for A1 real fast. So if we have A1, and let's go ahead and just figure it out. So this is a triangle. So automatically this means 1/2, right? Now, if you remember triangles, they work like this, right? It means that they have 1/2. And then here, right, we're going to take the length times the width. So here is delta V. And then after we have the other part is delta T, right? Because that's the width. So we have length times width. And that's going to get us the area of A1. Now, for intents and purposes of future parts, we're going to go ahead and actually take this out. And I'm actually going to go ahead and I'm going to part out delta. I'm going to part out delta V. So I'm going to make it V final minus V initial. And then after we got delta T. Okay. So that's A1. And actually, because I got this, let me go ahead and distribute 1/2 V final delta T. And then after we have 1/2 V initial delta T. Okay, so I'm just taking distributive property and I'm just kind of multiplying everything out. 1/2 distributes T, delta T distributes. So this is A1, okay? So this is what we got. This is actually not the hardest part. What's going to be harder is here, okay? And that's going to be here. Now, we have to think about this carefully, right? In this small space, right, we have length times width. Width is not a problem. It's the length that will be. So we're going to make an assumption, right? This is delta V. And if you remember the definition of delta V, it's V final, right, minus V initial, okay? It means that the top of my, the top of my square here, or my rectangle, is going to be V initial. The bottom of it has to be 0. In other words, this to this here is actually not delta V, it's just V initial, right? So it starts off with my V initial, okay? And then after my width, obviously, is still delta T. Okay, so I can go ahead and do that. So my A2, now I don't have any 1/2s here. This is going to be V initial times delta, and then after delta T, right? Okay, this does not look too bad. So you notice here we have this. So we got 2 V initials here and we got 2 V finals here. So what we're going to do next is we're going to add these two together. We're going to add A1 plus A2, and that's going to give us the total area under the curve. In other words, the total displacement that we have. Now, remember, displacement has this value, right? Delta X. I'm going to use this to my advantage right now. I'm going to go ahead and figure out these two. So it's A1 plus A2. So here we go. Here we have 1/2 V final delta T. Okay, and then after I'm going to do all v initial plus v initial delta t. Then minus 1/2 v initial delta t. Now, if you notice, these two terms are actually going to combine. And eventually I'm going to be left with this term, which is 1/2 v final delta t plus 1/2 v initial delta t, okay? Now this is all well and good, but you know what? We can actually take this further because, I mean, this gives us delta x, sure, but here's the thing. As I pointed out, we don't always have the advantage of knowing our v final, right? V final here is actually a bit of a problem. You see this here? Because although we can find v initial and we can get v initial quite easily, v final can sometimes be a problem to solve out. I don't want to actually be turning back to this equation all the time. But that's actually kind of a blessing here because we know this equation does work to find v final. Why can't we just go ahead and plug that into here? And let's see what happens. Let's go ahead and see what happens when we go ahead and plug in our v equation or equation of this line here in order to find our delta x. And if we go ahead and do that, I'm going to go ahead and do it here. Hopefully you guys can see it. Delta x, right? And we're going to combine and we're going to get v final. And we're going to just basically do this, right? We're just going ahead and we're plugging in this. So we're plugging in this into here. Okay, and this is actually what's going to make it kind of long. We get 1/2. You probably can see where I'm going. We get a t, or a delta t in this case, plus v initial, plus v initial, right? And we plug that all in, and then we get delta t. Okay, plus the 1/2 v initial delta t. Now, already this seems kind of long, but we still need to distribute. So I'm going to distribute 1/2 and delta t to here. You're going to notice I'm going to go ahead and get 1/2, right? Okay, and starting with this term, right? A, and then after we have delta t here and delta t here. Those are actually going to combine and make delta t squared. So this is delta t squared plus 1/2. Notice there's my v initial here. So v initial delta t. And then after we got another one here, which is plus 1/2 delta t. And as you can guess, those two combine. And now I have a whole again. So now I have 1/2 a delta t squared plus, well, now I have 2/2. That makes one whole. V initial delta t, right? Oops, I forgot the t here. Just realized that. Equals to delta x. Okay, now I can naturally rearrange this. And this actually makes, notice, this actually makes something that's correct. If you go ahead and do this, right, and we want to do it for our final position, I'm going to go ahead and actually do x final minus x initial, right? And if we want to find our x final every time, it will be 1/2 at squared. And I'm drawing over velocity right now, but you notice plus v initial delta t. And then after we go ahead and get x final, like 1/2 delta t. And notice we get a full-on polynomial here. And this is kind of our equation to find displacement when you have an acceleration involved. Do note, it actually is very similar to the one we used to find a displacement when a velocity is involved here. And it's actually using some of the terms, but notice the acceleration term, part of the acceleration term, basically they're all both the same, right? V initial delta t, right? Plus x initial, right? You notice that this term is actually the same. It's actually something we saw before when we were looking at displacement graphs. It's just that the acceleration was involved. In other words, that equation wasn't complete until we had an acceleration involved. But that acceleration term, when that was linear, when our x versus t graphs were like this, consider our acceleration was 0, so therefore that term didn't really matter. Now that it does matter, we have the full thing. All right, thank you guys for watching. Please continue and go on to part 4, where I go ahead and show you how to use this wonderful equation.